given Fourier transform of periodic signals. You can see there's a DC here shown when omega is 0. This pair of spikes here is indicating AC at a certain frequency, omega naught, plus minus omega naught. Then you have another amplitude of AC at a different frequency. Then it's 0 at over here, there's nothing. It's 0 at plus minus 2 omega naught and plus minus 4 omega naught. There are no signals. Then plus minus 5 omega naught, there's also a signal, AC signal. They usually come in pair when you represent them mathematically on this diagram. So now what we're going to do, we're going to pass the signals through a filter or HJ omega input.
Sir.
Yes.
For the right hand side, is that a negative 2 pi over 3, not a 2 pi over 3, sir?
Okay, it's 2 pi over 3. There's a typo error here. Okay, plus 2 pi over 3 on the right side. Thank you. There's an input, output. It's a linear time invariant system. So you're going to pass through the signal through a filter with various cutoff points. The cutoff frequency, the amplitude of the cutoff frequency is omega naught over 2. And it's going to be 0 elsewhere. If you guys remember this, for example, if I said the absolute value of x is less than 1, it means x is less than 1 or greater than minus 1. That's what it means. If x, for example, if absolute value of x is greater than 1, that means x is greater than 1 and x is less than negative 1. That's what it means. It's coming from your algebra classes. Okay. Using this knowledge, omega filter is on when omega is less than omega naught over 2 or greater than or minus omega naught over 2. So it's going to be 0 elsewhere. It's going to be 0 going to be 0 for omega naught over 2 greater than omega or when omega is less than omega naught over 2. Something's happening here. It doesn't write around here. I don't know why. Okay. So the signal is, it's filtering in this range, it's 1. It's not filtering, it's removing all the signals in this range. So now we go, so this is what we want to focus on. Focus on this, the signal, the filter amplitude is 1, that means it's filtering in this range. Come to this diagram here. So where is omega naught over 2? Is somewhere in the middle here. Omega naught over 2, omega naught over 2, somewhere in the middle. So you're going to filter the signal inside here. So what's inside this box that I just drew? G, what's inside the box?
Yes, sir.
Jessica, what's inside the box? Lim.
2 pi over 2.
Okay, 2 pi over 2. So what is 2 pi over 2? It's a what signal?
It's DC signal.
Good. So what the filter, as far as the amplitude is concerned, the filter has a magnitude of 1, and then it's filtering out 2 pi over 2. And that's going to be 1 over 2 multiplied by 2 pi. The inverse Fourier transform yj omega is yt, and that's going to be equals to so that's equals to what, Zfeng? Inverse Fourier transform DC at omega is 0. So what is the inverse Fourier transform of this? What is the inverse Fourier?
It's 1.
Okay. So therefore, the inverse Fourier transform of 2 pi located at omega equal to 0, the 1/2 is just a constant, it just stays there. So that's going to be yt is 1/2. So this is the frequency response 500 times e to the minus j 2/3 omega. So if the signal is made to pass through this system, y j omega is x j omega multiplied by h j omega. X j omega are all those signals shown from DC and all those ACs So we are not going to be writing this here. Because it's too much to write. So I'm just going to write this part here. E to the minus j 2/3 omega. So the inverse Fourier transform, what this part is doing, is doing is it's going to introduce a delay. So you can see from this table here, the inverse Fourier transform, this is the look at this, e to the minus j omega c. The inverse Fourier transform is a delay, a time delay. Okay. So what the time delay here means, so like this one means that there's a spike here at t equal to 0. But this one right here, it means there's a spike when t is equals to c. So there's a time shift or delay, we can call it. So using that delay, we take the Fourier transform of this inverse Fourier transform yt is xt delayed by minus 2/3. So therefore yt is xt minus 2/3. So of course, don't forget the 5,000 here. We had 5,000. So this is the delay. Any question? So all this output is telling that the inputs are shifted by 2/3 seconds. All the inputs are shifted by 2/3 seconds, except the DC is not affected. DC, all the AC that's time dependent is shifted by 2 seconds. Any question?
No.
Next one. The next one. So you just focus on this part here because this part is 0. Okay. So therefore I can just rewrite this hj omega is equals to e to the minus j 2 omega over 3. And omega is in between over 2, but more than minus 3 omega naught over 2. Then you have this delay, time delay. Okay. So you have two things to watch out for here. Now the filtering range is from minus 1.5 omega naught to 1.5 omega naught. So you go to your, so if you look, we'll take off the previous one. One 1.5 omega naught is somewhere here, right? 1.5 minus 1.5 or minus 3/2. And this is plus 3/2 omega naught. The filter going to capture everything that's inside here. So it's going to capture the DC plus the AC signal at omega naught. So this is going to be delta T minus 2/3. Therefore, okay, let me rewrite this. Y j omega is x pounds of the filter. So what do you have for the DC is 1/2 the DC is 2 pi over 2, right? It's located at omega 0. The DC. This is the equation for the DC. Equation for AC is 2 pi over pi. That's the amplitude. That's amplitude 2 pi over pi. Amplitude 2 pi over pi multiplied by the location of the signal is at plus minus omega naught. We have a time delay. Sorry. This is in frequency domain, e to the minus j 2/3 omega. Take the inverse Fourier transform of this. You got any question? And then we have to multiply by this e to the minus j 2/3 omega. Now you take the inverse Fourier transform. For multiplication, I just put a dot here. I'll take the inverse Fourier transform of this. Inverse Fourier transform we did this part earlier. The inverse Fourier transform of this part is 1/2. Same as we have done this before, the previous problem. So on this side is 1/2 plus this whole thing right here. Inverse Fourier transform is cosine omega naught t, right? Inverse Fourier transform. So it's going to be 2 pi 2/pi cosine omega naught t. And close. And then you also have a delayed by minus 2/3 seconds. So you can go ahead and rewrite that as and DC is not time dependent, so you cannot delay it. For the AC part, you have time dependency. So you're going to only delay that part. And this is a DC with an amplitude 1/2 plus an AC with an amplitude 2/pi. Frequency is omega naught, and there's a phase shift. Usually this part here, right here, there's a time shift, time delay. But when you multiply these things, it become omega naught t minus omega naught 2/pi 2/3. So when you multiply this, then you will get the phase. This is the phase, theta. Frequency times time. But for now, you can just leave the word just to tell you the difference between representing as a time shift and phase shift. I was just showing you that. Any question? Any question, guys?
No, sir.
No.
Please check and see if I have done any mistakes. So the one more. After that, we are done. Then I'll give you the mini project. So what this means, you guys know, right? The filter is going to be on from omega naught minus omega naught over 2, right? From here and then onwards, and then here omega naught over 2. So in this region, it's going to allow the signals to go through. Signals will be passed through. This is the pass band. So what's here in the middle? When omega is 0, is getting filtered out, which is happen to be 2 pi over 2. The DC, only DC is get filtered out. Go back to this diagram. So omega naught over 2 omega naught over 2 minus omega naught over 2. Then it's omega naught over 2. So that means you won't be receiving DC. DC get filtered out. But all the others are accepted, all these accepted. Mathematically speaking, all this, the one circled is going to pass through the filter. The one I just cross out, the DC, is not going to pass through. So therefore, so y omega is the input multiplied by the filter, the frequency response of the filter. This is just 1. Okay. So the inverse. So what's going to go through? What's going to go through is just the and then minus the DC part. All the signal is going to go through except the DC ray, which is happened to be 2 pi over 2, 1/2, 2 pi. The Fourier transform of this is xt minus 1/2. All the AC signals go through except the DC. So you guys have to know this for the exam. When you're training, sampling, all these things, you have to know.